In this screencast, we are going to talk about how to find stereogenic centers and then how to label them when you're naming organic compounds. So to locate a stereogenic center, you need to look at each tetrahedral carbon atom in a molecule. So you need to look at each tetrahedral carbon atom in a molecule. And you need to look at the 4 groups, not just the 4 atoms bonded to it, okay? If those 4 groups are different, it's a stereogenic center. That's it. Now, you can always omit from consideration any carbon with a double or triple bond every time, okay? So when we look at this stereogenic center, it's really easy to see those are 4 different groups. But when we come over here and look at this center, what we see is that this is a carbon and this is a carbon. So if we were just looking at the atoms, we would say, oh, those are the same atom. But you have to look at the entire group around here, and we can see that that group is a ethyl group, and this group is a propyl group, and those are 2 different groups, okay? And you can see them written here that those are different groups. So that's also a stereogenic center. Now, larger organic molecules can have so many stereogenic centers, so you do have to really kind of watch what's going on. You also need to make sure that you can look at this and say, for example, this one, and say, hey, look, I know that the stick structures or skeletal structures don't show that we have hydrogens. And there's a hydrogen atom right there. So here's some examples of common molecules, and their stereogenic centers are shown in blue. Now, when you have a stereogenic center, it's quite possible that you could have an enantiomer. So enantiomers are non-superimposable, mirror image molecules. Okay. Any molecule with one stereogenic center exists as a pair of enantiomers. Okay. Now, a lot of times you may be asked to draw the enantiomers of a chiral carbon or a chiral compound like 2-butanol shown here. Just when you're doing the first one, you need to just kind of arbitrarily place the 4 groups on any bond, and then you just draw the mirror image here. So there's a hydrogen on the dash back, there's an OH here, the CH3, and the CH2CH3. And so that's a way to draw the molecule and then the mirror image. Now, I want us to do an example of this. So let's look at, right? There are 2 ways you can draw an enantiomer, right? The first way, which we already talked about, is you draw as a reflection. Ooh. We can draw this molecule okay? And so this is 3-bromohexane. Okay. So I'm going to come in here, right? and start here. And then from this, I'm going to draw the bromine. And then the hydrogen goes here. And then you go down like that. And you can see where if there's a mirror here, that would be the reflection. The second way to do this is to invert the configuration of a stereogenic center. Okay, so when you do this, we have, for example, the 3-bromohexane again. What you're going to do is you're going to switch the groups on the dash and wedge. And these are the front and the back groups. Okay. And so now these are enantiomers of each other. This is the 3-bromohexane, and this is the enantiomer. The positions of the carbon along the chain here, or whatever is going to be here, always stay the same. The only thing you change are what's on the dash and the wedge. You can also have stereogenic centers in cyclic compounds. So, for example, we see here, this is methyl cyclopentane. And the big hint here is you always need to draw the rings as flat polygons. And then that will help you look for the tetrahedral carbons that are bonded to 4 different groups. So when I look here, I can say, okay, right, we have one group here, and I know we've got a hydrogen, and that's a different group, but what do I do about the ring? If the 2 groups are equidistant from the carbon, then those count as the same groups. And so that is not a stereogenic center. When we look here at 3-methylcyclohexane and we look at that carbon is a stereogenic center because we have 2 different groups, because this double bond here makes it different. Okay. So then when we come down here, we can draw the enantiomers like this, right? Or you can still flip and do the inversion like we did on the previous slide. I want to talk a little bit about some biologically active molecules with stereogenic centers on their rings. When we look at this, this is the molecule thalidomide. It was prescribed as an anti-nausea drug in Europe and Great Britain in the 50s. So a lot of women took it when they were pregnant in the first trimester and had lots of nausea. And the problem was that they were given a racemic mixture. And so while this worked as an anti-nausea drug, this attacked rapidly dividing cells. And so you had babies born that didn't have arms and legs. And so that really emphasized the importance of having drugs where they were either enantiomerically pure, or you knew without a shadow of a doubt what both enantiomers, the effects would be. I also want to point out these 2 compounds. This is sucrose, which is table sugar, and this is Taxol, which is an anti-cancer agent. These are 2 really useful compounds with several stereogenic centers. in their carbon rings. And so we can determine stereogenic centers if we just go systematically through a molecule and identify them one carbon at a time. So sucrose, for example, has 9 stereogenic centers, and then Taxol has 11 stereogenic centers. Now, since enantiomers are 2 different compounds, they need to be distinguished by their name. And so the way that we do this is we label them as R or S. And to designate R or S, we need to first assign priorities based on their atomic number. So we have some rules to follow when we do this. And the first rule, right, is to assign priorities in order of increasing atomic number. The atom with the highest atomic number gets the highest priority, which is 1. Okay, so for example, if we pull out our friendly periodic table, we see that the atomic number for hydrogen here is 1. And then we go to bromine, and the atomic number of bromine is 35. And then chlorine is 17, right? And fluorine is 9, right? Those are the atomic numbers. And you can see, right, the atomic number of 35 is 35. That's the highest, so that gets the first priority. Chlorine gets the second priority at 17. Fluorine gets the third at 9. And then hydrogen gets the last at 1. Okay? And so that's our first thing that we do. Okay? Now, sometimes this worked out lovely. They all have different atomic numbers. So when you come down here and look at these atomic numbers, we have oxygen, which has an atomic number of 8, right? And then, of course, hydrogen, which has an atomic number of 1. But both of these carbons have an atomic number of 6. And so the question is, well, what do you do? Because there's a tie there. So if there's a tie, then you need to assign priority based on the atomic number of the atoms that are bonded to these atoms. So you move to the next set. So if there's a tie, so when we look at this, we're going to look at what this carbon is bonded to and what this carbon is bonded to. And so we find with that CH3 here, that carbon is bonded to 3 hydrogens. This carbon is bonded to another carbon here and 2 hydrogens. And so these here, these basically cancel, right? Because those equal each other out. And so this carbon is a higher priority than the hydrogen, so that becomes the second priority. Now, for rule 3, sometimes you're going to have isotopes, right? So if you have 2 isotopes are bonded to the stereogenic center, assign priorities. In order of mass number. Where we really see this is hydrogen versus deuterium, where deuterium has a mass number of 2, so because it's got 1 proton and 1 neutron, so it's got a higher priority than the hydrogen atom here. Then finally, kind of this last rule is, what do you do with multiple bonds, right? So to assign a priority to an atom that's part of a multiple bond, treat the multiply bonded atom as an equivalent number of singly bonded atoms. So, for example, right, if we were looking at the priority here and we have a C double bond O, right, this would be the equivalent of this carbon being bonded to 2 oxygens, okay? And then the oxygen is also bonded to 2 carbons. For example, here, when we look at the double bonds, here, it's like this carbon is bonded to carbon twice, and then this one is bonded to carbon twice, okay? Same thing with the triple bonds. It's like this one is bonded to a carbon twice, and then this one is bonded to a carbon twice. So that's how you figure out, if you're trying to figure out the equivalence there, that's how you do it. So I want us to do some examples, okay? So let's look at this molecule. And what we're going to do is we're going to find the stereogenic center, and then we are going to assign the priorities. So I start off here, and there's oxygen. That's not a carbon. This carbon has 2 hydrogens, so those are the same 2 groups. This carbon has this, and those are different, and then OH and H is different. So that's my stereogenic center here, and I can put an asterisk there, and a lot of times that indicates a stereogenic center. Then I'm going to look here, and that's got a double bond, so that carbon doesn't have one, okay? And so now I'm going to assign priorities. It's pretty easy to assign the priority for hydrogen. Hydrogen is going to be 4. It's going to be really low, right? And then I want to look at the other atoms that I'm assigning. So this, when I look at the atom that's right here, that's a carbon that's there. And then we have an oxygen here and then a carbon here. So that leads me to believe that that oxygen is going to have the highest priority. And so I've got 1 and 4, but I'm trying to decide between 2 and 3. So I need to think about what this carbon and this carbon, like what bonds they have, okay? So when I do that, this carbon is bonded to a hydrogen, and an oxygen. So there's a carbon here, and there's a hydrogen, and an oxygen here. This carbon right here is double bonded to an oxygen. So that's like saying, look, It's bonded to an oxygen and it's bonded to an oxygen. That's from the double bond. So we list it twice, and then it's bonded to another oxygen with the OH group. So those oxygens cancel, and we can see here that this oxygen is going to be a higher priority than the hydrogens are. So that means this then would be 2, and this would be 3. And so that's a way that you go through and you assign priorities. Now, once you have assigned priorities, we can assign if things are R and S. So to assign R and S, to label these enantiomers, we need to follow a few steps. So this is an example. We're going to label the enantiomers shown here as R or S. And the first step is you assign priorities. Right? So when we look at this and assign priorities, hydrogen here is 4. The oxygen is 1. Both of these are carbon. This carbon's bonded to 3 hydrogens. This carbon is bonded to another carbon and 2 hydrogens. So it's going to end up being 2, and this will be 3. And so those are our priorities that we've assigned. Okay. Then we go to step 2. And in step 2, we need to orient the molecule with the lowest priority group on the back dashed wedge. Okay. And when you do that, when you push this guy back, that makes 1, 2, and 3 come to the front, and you need to just visualize those. Okay. And so, for example, if we've got this here, we're just doing 1, 2, 3 here, right? If we're looking at the other one, right, where the OH is back here, then it's 1, 2, 3 this way. Okay. Then we need to trace a circle from 1 to 2 to 3, right? If it goes in the clockwise position, that's the R isomer, and if it's in the counterclockwise position, that's the S isomer. The easiest way for me to remember this is you turn the steering wheel to the right in the car to turn right, okay? And so that's the R isomer there. So then you would name, right? This molecule as R butane 2-ol. And we have not talked about this business yet, so don't panic about that. But what I want you to notice is because it's the R enantiomer, the R goes in the front in parentheses here. And then the other enantiomer right? That's the S enantiomer. We would say, look, that's S with those parentheses, then a dash, butane 2-ol. And so that's what we see there. So I'm sure the burning question in your heart is, Dr. Pierce, what if the lowest priority group is not on that hatched back wedge? What do I do? It's a great question. The first thing you need to do is you need to switch the lowest priority group with what is on the hatch wedge. That's the first thing. Then you need to determine R or S in the usual manner. And then you need to reverse the answer. So let's do an example, okay? Let's say I've got this molecule. Right? And I want to know, is it R or S? I come here and I assign my priorities, just like normal. And I say, okay, hey, look, there's oxygen. That's going to be my highest priority. I have a carbon here, and a carbon here, and a carbon here. This carbon is bonded to one other carbon. This carbon is bonded to two other carbons, and this one is just bonded to hydrogen. So that means this one bonded to two other carbons is going to be my next highest priority. This is my third, and then that's my fourth. Okay? So when I look at this, I say, okay, I need to switch 4 here and 1 here. Keep 3 and 2 the exact same. Okay? So when I do that, so I start by drawing the things that don't change. And then on the hatch here, I put the hydrogen. And then on the straight line here, I put the OH. And then I just go back with my priorities. 1, 2, 3, 4. And so I see from 1, 2, 3 that this goes to the right. So this is the R. That means the original is S. All right, we are going to do some more of this in class where we work some problems. If you have questions, please stop by and see me. And of course, at the end of the syllabus, there are some extra questions that you can work and extra problems. And I really, really encourage you to work those so that you are familiar with naming enantiomers.